Hello everyone, my name is Isaac Montoya and I'm the Marketing Coordinator for Upside Technologies. I will be moderating today's webinar and thank you so much for joining us. We are Upside Technologies, and if you are unfamiliar with us, we are known as the pioneers of data center airflow management. We were started by Ken Brill in 2001, and you may also know Ken Brill from founding the Uptime Institute. We have deep roots in airflow management, science, and history, and we are pleased to share that level of knowledge with you here today. You may also know us by our products. Our first product was the Cold Lock Integral Brush Grommet, which essentially started the whole airflow management movement in data centers back in the early 2000s. And since then, we have launched our line of hot lock blanking panels, aisle lock modular containment, and most recently our energy lock line of environmental monitoring solutions. So today, I am glad that you have joined us here today because we have declared June as Airflow Management Awareness Month. What we have seen in the industry is that there's still a lot of issues around the topic that exists and a lot of misinformation. This month we have hosted a series of webinars to help correct a lot of that misinformation and really to help educate and empower managers and operators of data centers. With that being said, today's topic will focus on data center cooling efficiency and understanding the science behind the 4 delta T's. Today's webinar will be presented by Lars Strong. Lars is our Senior Engineer and Company Science Officer here at Upside Technologies. You may be familiar with him from speaking at many industry events around the world. He regularly authors topics in this space and presents at many events every year. So without further ado, I will pass along to Lars.
Thank you very much, Isaac. Well, I'm really happy to be sharing this webinar with you and talking about this topic in particular because I think it's really a helpful way to get a hold on what's happening in your computer room. There are a lot of myths, a lot of half-truths, a lot of people going around in the industry these days saying this is the way to approach it, this is the way to resolve and fix airflow management, this is the way to be more efficient. Hot aisle containment is best, cold aisle containment is best, all of these kinds of things. But what I've always focused on in my career is really explaining the science behind the cooling and the science behind the best practices. And so this is a topic that we've developed over the last couple of years. Just begun presenting this at a few events recently, and I'm really excited about the insight that this awareness can have. So, without that, without any other ado, we'll get into it. We'll cover the concept of delta T's, the definition, talk a little bit about PUE and bypass airflow. I talk about these at just about the beginning of every single presentation I do because understanding bypass airflow and why we're doing this is really crucial. And then we'll get into the more commonly known delta T's, the less commonly known ones, and then how to apply this awareness to improving conditions in your room. So delta T, of course, means the change in temperature, and from one location to another. And the temperature of the air, in this case, we're talking about air as it moves around, flows around in the circle of the room. The temperature is only going to change if heat is removed or if heat is added, or if warm air mixes with cold air, there's going to be a change in temperature of the combined flow streams of air. And it's really interesting when you ask people about delta T. It depends on who you're asking. If you ask a facilities person, they're likely going to tell you about the delta T across the cooling units, across the cooling coils, or maybe the delta T of the chilled water. Or maybe even the condenser water, or something that's happening out further from the computer room. But if you talk to an IT person, ask them what delta T is, they're going to most likely refer to the delta T through the IT equipment. And all of these are important and valid, and understanding how they relate provides a lot of insight. So, while many people think there's just one delta T, and ideally there should be just one, there are actually 4 in computer rooms, in all computer rooms. And so we'll get into those. Here's a little schematic that shows what they are. This is the air flowing around in a loop. It passes through, comes out of the supply tiles in a cold aisle, passes through the IT equipment, and that's where the temperature changes for the first time. Increases as heat is added to the air. Then there's a temperature drop returning to the cooling units. Then there's a further temperature drop as the air goes through the cooling units. And then there's the temperature difference from where the air comes out of the cooling units over to where it goes into the IT equipment. And so 1 and 3 are obviously the common ones, and 2 and 4 are the ones that can provide a lot of insight if you go and measure those and understand what's happening in the room. So why are we talking about all this? Well, PUE is a fundamental metric in the industry, of course. Probably everyone on the call has heard about it. If not, there might be a few of you that have not heard of PUE. It stands for Power Usage Effectiveness. It's very simple to calculate once you have the information. In a mixed-use facility, it can be hard to get a hold of some of the data. Basically, hard to get a hold of what is the total load supporting all the data center equipment. But when we break it down and we look at it, it becomes really obvious that cooling provides the greatest leverage. While there might be a very good ROI and for increasing the efficiency of the IT or of the electrical equipment, say changing from one UPS to a more efficient UPS, that generally represents a pretty small portion of the pie. This chart represents a PUE of about 2, which is still somewhere around the industry average, maybe a little bit lower than that. But when you look at this, we see that the mechanical plant and the cooling fans, basically all the cooling equipment, represents 35% of the total load or 73% of the non-IT load. So whether these numbers represent your side or not, they do represent the significance of the importance of improving airflow management and cooling efficiency. Here's some data from the last 45 sites that I've looked at, and you see a number of different metrics that I've looked at here: the total area of the room, the number of running cooling units, the raised floor bypass open area. This is just how well are the holes in the raised floor managed. Found that only 48% of the openings in the raised floor were in a bad location, meaning the air coming out of those openings was wasted behind equipment and just directly returned to cooling units as bypass airflow. And then something as simple as properly placing the perforated tiles, only 77% of the tiles were in the proper location. And out of 45 sites, I only found 6 that I would say had placed every supply tile in an appropriate location. Most of the sites I found, 39 of them, there was a supply tile somewhere where it shouldn't be, out in a hot aisle or open space. So these are all creating opportunities for efficiency. And most significantly, you see the last column there on the right, the cooling capacity factor. That's a metric that we developed to estimate the utilization of the cooling infrastructure in the computer room. And we've written a white paper on that. There's a lot more information about that. But basically, it shows that 3.9 or nearly 4 times more cooling unit capacity was running in the room than was required for the IT load. That's most often due to very poor airflow management. So a lot of opportunity to get that number down. All right, let's get into bypass airflow, the last thing to cover before we get into the delta T's. The definition of bypass airflow is simply any conditioned air that comes out of a cooling unit and does not pass through IT equipment before returning to a cooling unit. So in this graphic, we see all the cooling units are represented by this one cooling unit. All the IT cabinets are represented by these 2 rows. So it's all simplified down to one cooling unit and 2 rows of equipment. And all the numbers on here and the arrows represent the volumetric flow rate of conditioned air through the room. So whether that's cubic feet per minute or liters per second, doesn't matter. We're just going to consider the relationships here. So we have 10 units of air moving through all the cooling units going under the floor. So 10 units of air is going to come out of the floor. And in this example, we have 6 units coming out of cable openings behind IT cabinets or under IT cabinets, 3 in each row. And we have 4 units of air coming out of supply tiles in the cold aisle. And we see the 2 represented by arrows passing through the IT cabinets. So each row consumes 2 units of air, so all the IT equipment in the room consumes 4 units of air. That's the demand of the IT equipment. Well, we're supplying 4, so the IT equipment might be happy. There's enough of it. But there's 6 units of bypass airflow. There's 6 units more air moving through the room than demanded by the IT equipment. So the misconception here is that a lot of people feel that by sealing those cable openings, they'll reduce the amount of bypass airflow in the room. Well, it's a good thing, of course, to seal those openings and direct the conditioned air where you want it into the cold aisle, but it doesn't change the amount of bypass airflow in the room. Now we have 10 units of air delivered to the cold aisle, but the IT equipment still only requires 4 units of air. So 6 units of air leave the cold aisle as bypass airflow. And this would be true whether there were containment or no containment in place. Until you reduce the amount of air flowing through the cooling units, you're not going to change the amount of bypass airflow in the room. Airflow management at the rack and row level might change the amount of bypass airflow at the cabinet level, but it won't change the amount of bypass airflow at the room level. All right, let's get into the delta T's. And I encourage you to keep note of your questions, and particularly anything that I say that you might disagree with. We'll have a chance for you to use the chat box in the lower right-hand corner of your screen with the webinar software to type in any questions that you have, and we'll have some time to go through those at the end here in just a few minutes. All right, so the most common one is the change in temperature through the IT equipment, represented here with the 1. And that's as air passes through the IT equipment, energy is added in the form of heat, and the temperature of the air increases. And there is a fixed relationship between the amount of heat that is added to the air, the flow rate of air, and the change in temperature. That's that last bullet point. And every kilowatt of electricity consumed by IT equipment becomes a kilowatt of heat added to the flow of air through the IT equipment. And this is the case regardless of the airflow management in the room. So in simple terms, whether the air going in is 70 degrees or whether it's 50 degrees, the same amount of heat is going to be added to that air, and the same temperature increase will result as it moves through the IT equipment. There's a caveat to that, which is as the air temperature increases to a point somewhere between 75, 80 degrees, maybe a little higher, a little over 80 degrees, then the IT equipment is going to have a hard time cooling itself with that given flow rate. So the fans in the IT equipment are going to speed up, and that might affect the delta T of the IT equipment a little bit. But it's the same kilowatts of heat being added to that conditioned air. So this heat transfer equation is a simplified version for the units of measure that we are familiar with in North America, degrees in Fahrenheit and flow rate in cubic feet per minute. But this equation can easily be simplified, not this equation, but the heat transfer equation can easily be simplified for metric units as well. So if we know any 2 of these variables, the flow rate, the delta T, or the heat, we can calculate the third. And this plays out in a significant way in affecting how much airflow the IT equipment is demanding. IT equipment manufacturers are striving to make their equipment as efficient as possible. And one of the ways that they're doing that is by reducing the amount of energy consumed by the fans. So they're slowing the fans, the cooling fans in the servers down and designing for a higher delta T. If the air is moving through the server more slowly, then it's in the server longer and it has longer to heat up, and the delta T will be higher. So older legacy equipment, 3, 4, 5 years old, will have lower delta T's, and more modern equipment is being designed for higher delta T's. Also, there's a factor which is how much the IT equipment is being loaded. If a lot is being asked of the equipment, then it might be working harder and adding more energy to the air. But this can have a very significant difference. As you can see, with just a 15-degree delta T, 211 CFM are required to cool 1 kilowatt. Whereas if the delta T is 40 degrees, then 79 CFM is all that's needed to remove 1 kilowatt of heat from that IT equipment. So when you're really refining and balancing airflow management in the room, this knowledge becomes really important. Here's an example. Blade servers, 1U servers tend to have a higher delta T, 35 degrees, and they're going to consume about 90 CFM per kilowatt. Or not the 1U, the blade servers, pizza box or 1U servers, or any equipment with a 20-degree delta T is going to consume about 158 CFM per kilowatt. And so one way to use this awareness is to look at your UPS load, and the best thing to do is to go around in your room and measure what the delta T is of your IT equipment, and come up with what's the average delta T through the IT equipment. If there's a huge mixture of equipment in the room, this can be a lot more challenging. If it's much more homogeneous, then it's a much simpler task. You can take that delta T, determine what the CFM per kilowatt is, and multiply that times your UPS load, and you'll know the total IT demand of cooling. Another way to look at it is just assume that it's about 100 CFM per kilowatt, about a little more than a 20-degree delta T, and just take 100 CFM per kilowatt times your UPS load, and that's the approximate IT cooling demand. And then you can subtract this from the total flow rate through your cooling units, and that's relatively simple to determine from the specifications of the cooling units for the fan speed and the fan motor size that you have, and actually calculate what is the bypass airflow rate in the computer room. And these numbers can be really revealing. The goal is to get that as close as possible, get the flow rate through the cooling units as close as possible to the flow rate through the IT equipment. Maybe somewhere in the order of 20% extra cooling flowing through the cooling units than the IT equipment. But in a lot of rooms, there's 4 times more or 400% more air flow rate through the cooling units than the IT equipment. So I encourage you to look into these numbers. All right, a little bit more on the commonly known. The other one is through the cooling units, obviously where the air temperature is dropping as heat is removed by the cooling unit. And this drop in temperature is affected by what type of cooling unit you have. Legacy DX units have traditionally been fixed at about 18 degrees Fahrenheit. So if they're removing 18 degrees of air, of heat, then that might be more than the cooling unit needs to remove to maintain a certain air temperature. And so after a little while, the air is going to get colder than it needs to be, and then it's going to shut off or go to a lower stage. A lot of DX units operate at 0, 25, 50, 75, 100% capacity, so 4 steps. And if one step is too much, it'll run at that step for a while, and then it'll step down. Whereas chilled water units have a much finer range, that chilled water valve is closer to infinitely adjustable and can more consistently match the heat load that is being required for it to be removing. And then we talk about, and ASHRAE talks about raising temperatures in the computer room and the benefits of the mechanical system becoming more efficient. As the return air temperatures increase, the cooling units actually can deliver more capacity, and that's represented by this fact that if you increase the return air temperature to the cooling units by 5 degrees, you might only see a 3 or 4 degree increase in supply temperature. So it's actually getting more heat out of the air, doing it more efficiently. Therefore, it doesn't need to run as much. I already talked about how chilled water cooling units have a much wider range of delta T. They also have a much wider range of fan speeds that they can operate at because they're not worried about freezing up. So, while DX units are very convenient and easy to retrofit, there are some advantages to chilled water units. Now, I spoke about trying to match the flow rate of the conditioned air to the flow rate of the IT air. That's only possible if the delta T that the cooling units can deliver is the same as the delta T of the air moving through the IT equipment on average. So as IT equipment delta T's are increasing, there are leading edge people at the the cutting edge of this, at the cutting edge of efficiency. There are data center designers working with cooling unit manufacturers to match the delta T that the cooling units deliver with the delta T of the IT equipment so that the fan energy savings can be maximized as much as possible. So those you probably know of quite well, but let's talk about the less common ones and the ones that really can provide some insight. And the first one is the decrease in temperature of the air coming out of the IT equipment before it returns into a cooling unit. So why would this air drop in temperature? It's obvious. The only way for the temperature to drop is for cold air to be mixing in with that hot exhaust air. And this is the result of bypass airflow. There's conditioned air that's not passing through IT equipment, not getting warmed up, but it has to mix with the hot exhaust air coming out of the back of the IT equipment before returning to the cooling units. And it has to do this regardless of the airflow management in the room, regardless of containment. That air all has to come back together and get through the cooling units before continuing its cycle. So what do we see? We see coming out of the back of the cooling units, represented here in bright red, quite often somewhere around 95, 100, or even 110, 15 degrees coming out of the back of the IT equipment. But it's not uncommon to see cooling unit return air temperature set points in the high 60s or low to mid 70s. So why is the air temperature dropping 20, 30 degrees from the time it leaves the equipment just by the time it gets back to the IT equipment? Well, as I said, obviously, a lot of conditioned air is mixing in and reducing that air temperature. It could be, as we see here, that blue arrow coming out of the floor, represented by representing bypass airflow coming out of unsealed cable openings. It could be excess conditioned air in the cold aisle, wrapping over the top of the cabinets or around the ends of the rows, or conditioned air coming out of the openings under PDUs. PDUs are wasting more conditioned air probably than any other single element in computer rooms around the world today. So this extra air, if it's flowing out of cooling units, it's going to get back to cooling units no matter what you do in the room. So you need to improve airflow management first so that you can then reduce the flow rate of conditioned air and reduce how much air is mixing, and then you'll be able to raise the set points and reduce the delta T of this number 2 of this the air before it goes back to cooling units. Here's an example showing this real clearly. This is an infrared image. I took this standing on a ladder in a computer room looking down on the top of a cooling unit. So we're looking at the filters, and we see a nice patch of really warm 85-degree air flowing into the center of the cooling unit, and some bypass airflow around the edges, some 10 degrees colder air flowing into the edges. And what's happening here is that there's a hot aisle there to the left. You can see 2 rows of cabinets, and there's some nice hot air coming out of that hot aisle flowing back to the cooling unit. But there's also a bunch of bypass airflow. There's too many perforated tiles in front of the cabinets, and that cold air is flowing back to the cooling units without flowing through IT equipment. So we have these 2 distinct plumes of air flowing back to the cooling unit and showing up very clearly in red and blue. The 4th one is the change in temperature from when the air leaves the cooling unit to when it goes into IT equipment. And you would think, well, you know, obviously, why would the temperature increase? There's no heat there. The only reason temperature is going to increase is because there's hot air mixing in with that supply air before it gets to the IT equipment intakes. There may be a little bit of convection, a little bit of radiation, radiated energy adding temperature to the air, but that would only represent a couple of few degrees change in temperature. But very commonly, you know, we see supply temperatures in the mid to high 50s coming out of cooling units, maybe the low 60s, but the warmest intake temperature to IT equipment might be in the mid 70s or high 70s, low 80s, maybe even in the 90s in a couple of spots. So we're seeing a delta T in this 4th location of 20, 30 degrees when we shouldn't see any in an ideal world. I said, obviously, that's the result of hot air mixing in from some location, either missing blanking panels and the hot air is flowing through from the back of the cabinet, or around the ends of the rows, over the tops of the cabinets. There's some lack of airflow management in the room that is causing some mixing of air before it gets to the IT equipment. Okay. Most common way to deal with this is to supply more air and supply colder air to overcome the mixing. We see here in blue, dark blue, 55-degree air coming out of the cooling units, you know, warming up to somewhere in the mid-70s by the time it gets to the IT equipment. And as I said, that warm air could be coming from a number of different locations, around the ends of the rows, over the tops of the cabinets from adjacent rows, but there's some mixing occurring. Here's an image that, again, really clearly points out a variation in intake temperatures. And I want to take a moment just to say that intake temperatures to the IT equipment are paramount. And there's a lot of advice about raising temperatures and changing cabinet design or changing set point control or a myriad of different things in airflow management. But it all comes down to what is the intake temperature to the IT equipment? What is the desired maximum that your site has established for intake temperatures, and how even is that distribution? There's a direct relationship between how even the intake air temperature is to IT equipment, how consistent it is, and the efficiency of the cooling infrastructure. So the more consistent, the more efficient. There's a huge range in intake temperatures, which is very common, sometimes even in the same cabinet. The bottom equipment might have an intake of 60 degrees, and the top of the cabinet, the intake temperature is 75 or 80 degrees. You know, not uncommon to see a 15, 20 degree difference in intake temperature. This goes away, of course, with the more airflow management you put in. One of the benefits of containment is that the intake temperatures become much more even. So in this picture, we see an extreme example of the bottom half of the cabinet has intake temperatures below even ASHRAE's recommended minimum of 64. All that purple and black stuff is lower than 64 degrees. And the top half of the cabinet almost is above ASHRAE's maximum of 80 degrees. And there's this narrow band in the middle of 3 or 4 U that is actually the only location in these cabinets receiving ASHRAE's recommended intake temperature range. So, moving on, how do we apply this in computer rooms? Well, the goal, one of the goals to shoot for is that the less commonly known delta T's, that temperature difference from the supply to the intake to the equipment and from the exhaust back to the cooling units. The goal is to try and get that delta T as close to 5 degrees as possible, 5 degrees Fahrenheit. And I think if you go measure this, you'll find that in a number of locations, this is, double digits. And so getting it at least into the single digits and hopefully as close to 5 degrees as possible can dramatically improve the efficiency of the room. The way to do this is not to go change set points and increase temperatures in the room. The way to do this is to collect information. Find out what's going on about intake temperatures and what's causing the mixing, where the exhaust air is getting to the intakes, improve the airflow management, and then be able to make changes to the set points to be able to improve the efficiency and the capacity in the room. So monitoring is key. And when we start to improve the efficiency, we can dramatically improve it has a cascading effect on many things. So we improve airflow management, then we're able to raise temperatures, supply and return temperatures, and we're able to reduce the flow rate of air required to keep the IT equipment happy. This can have a dramatic impact on the number of hours that free cooling can be utilized in computer rooms. There's more and more sites going to some form of free cooling, and whether it's direct air economizers or water side economizers, improving the airflow management and then making changes to the controls affects all of those systems. And two of the most valuable tools for doing this are an IR thermometer or an IR camera, and using those to look at all the surfaces in the computer room. These tools are actually incapable of measuring air temperature, but they're capable of measuring the energy emitted by surfaces, solid objects. So we can measure the temperature of the cabinet faces, which is a likely indication of the air temperature of the conditioned air moving into the IT equipment. We can look at the temperatures at the backs of IT equipment. Another useful thing is to look at the ceilings above cold aisles. And if there's no containment present and the ceiling is cold, then there's very likely more conditioned air delivered to that cold aisle than required by the IT equipment. So there's bypass airflow flowing straight out of the cold aisle, going up, hitting and cooling the ceiling. As I showed you that picture, take a look at the tops of cooling units and see if there's a mixture, a variation in air temperature. Quite common to see computer rooms designed with corridors for cooling units and have big grills in the sides of the wall for that return air to get back to the cooling units. I've identified a lot of problems by looking at the walls and those grills where the air is returning to cooling units. Another valuable tool in this process is a methodology we've developed that we've coined as the 4 R's of airflow management. And it helps us to remember that there's really 4 pieces to this process. There's managing the airflow at the raised floor level. There's managing the airflow at the rack level, the row level, and then making adjustments to the room, to the controls, to be able to realize those savings. We've developed a video on this that presents some really nice visuals that may be real helpful for you when discussing this and showing this and explaining these concepts to others in your organization. And real simply, the raised floor is managing the openings in the raised floor so that cold air is only entering through the supply tiles located in front of IT equipment where you want it to, and that there's no unsealed cable openings, there's no perforated tiles out in front of the door, so that the managers and the board of directors feels comfortable getting a blast of cold air when they open the door and take a look in the room. Perforated tiles are only where they should be. The rack, that vertical plane across the front of IT equipment, should be sealed up so that the only way for air to pass through the cabinets is through the IT equipment. This also applies to underneath the cabinets. We're seeing a lot more evidence in visiting sites that there's air flowing underneath the cabinets. Quite often it's exhaust air from the hot aisle flowing under the cabinets, coming into the cold aisle and elevating temperatures. Then, of course, making improvements to the row level. This involves sealing spaces between cabinets and putting in containment. And as I'll show you here in a moment, full containment is not always necessary. There's just enough containment to prevent the airflow wrapping around the ends of the rows or over the tops of the cabinets is all that's required to be able to achieve an efficient system. And then once airflow management is improved at any one of these 3 levels, you can make changes to the room level to maximize the benefits. So if a rigorous effort is made to seal cable openings and openings in the raised floor, then you can go right to the room level and see how much you can reduce fan speeds. And then after installing, say, blanking panels in every cabinet, you can then go see how much you can raise temperatures at the room level, make changes to the controls to realize the benefits. So here are the product lines that we've developed to address each of these areas. Our Cold Lock product line has a wide range of products to seal openings in the raised floor. That upper right-hand, one in the upper right-hand corner is an extended brush, and I point that out because it's probably our least utilized product and our most flexible, particularly for sealing large openings underneath PDUs and other infrastructure equipment. Then our Hot Lock product line is a number of different ways to seal openings in the rack, between the rails and the sides of the cabinet, as well as pass-through blanking panels that have brushes so that you can pass cables from the front to the back and seal that opening. Then we have our products to address the row-level airflow management, our aisle lock modular containment, and all of these products attach magnetically, magnetic attachments of doors and baffles to either go on the hot or the cold aisle. And our most recent line of products is our Energy Lock room level monitoring, wired and wireless and leak detection. And as I mentioned, of course, you got to collect information on what's happening, where the temperatures are the highest, where they're the lowest, and make efforts to improve those. It's been said that it's impossible to purchase efficiency. Efficiency has to be managed. It can't be bought. There's no silver bullet out there. There's no product that exists that you can just buy and install that is going to give you efficiency. It's going to give you the opportunity to improve efficiency. So I hope that I've provided some information that is new and valuable to you. Look forward to your questions here in just a minute, but I'll hand it back over to Isaac to wrap up.
Thank you, Lars. Yeah, before I wrap this up, I'd like to encourage you all to start submitting your questions. For those of you who haven't already done so, you can do so in the bottom right corner of the control panel. In the meantime, throughout this entire month, we have hosted a series of webinars on airflow management. And for those of you who this is your first one, I would encourage you to go back and watch our recordings to view various topics such as, science behind airflow management, myths of containment, and how IT decisions impact facilities management to optimize your data center cooling efficiency and airflow management. So with that being said, I would like to thank you all for joining us in our webinar today. We will now get to the questions. Before so, you will see Lars Strong's email there where you could, if you have any questions, feel free to reach out to him. And we also put out a lot of content on our social channels as well as our blog. So please follow us and subscribe to our blog to stay up to date on most recent news and trends in airflow management and data center cooling best practices. All right. Okay, we will go to our first question.
All right, thanks, Ed. Is it a way to, the first question is it a way to measure the PUE online? Well, I believe the understanding your question, absolutely. There's a number of different building management systems and data center infrastructure management, or DCIM, solutions that enable you to see what's happening with a number of different things in your facility, particularly PUE, and log in and gather that information anytime you like. If that's not what you were addressing, then please clarify and I'll be happy to answer. Yeah. The other, so PUE is a really valuable tool, and it's the first metric, if you're not calculating, that you should calculate to determine the efficiency of your site. But it doesn't tell you where the inefficiency is. The cooling capacity factor metric is the next metric that I would recommend calculating to understand what the utilization is of the cooling equipment in the computer room. And that provides a lot of insight into how much opportunity there is. Another question here, how do you address a 35-degree delta T for blade servers if your AC system can only provide a 20 to 22-degree delta T for cooling? Will the room gradually heat up? Great question, Tim. The way that works is, even if there are way more cooling units running and installed in the room than necessary to support the load, the amount of heat being removed from the room pretty much always equals the amount of heat being added to the room. Computer rooms very rarely are heating up, only when there's a failure of some sort. But under normal conditions, they're steady state. There's slight variations, but they're basically considered a steady state environment. And that means the amount of heat being added equals the amount of heat being removed. Otherwise, yes, the temperature would be increasing over time. So, because there's a difference in delta T between your IT equipment and your cooling units, doesn't mean the room is going to heat up. What it means is that more air is required to flow through your cooling units than flows through your IT equipment. So I'll make an extreme case just so that I can paint a clear picture. If the delta T through the cooling units was only 20 degrees, and the delta T through the IT equipment was 40 degrees, twice as much, then there would have to be twice as much air flowing through the cooling units than flowing through the IT equipment. So if all the IT equipment had a demand flow rate of 100 CFM, then there would have to be 200 CFM of air moving through the cooling units. So 200 CFM of air comes out of the cooling units, and half of that air goes through the IT equipment and warms up 40 degrees, and half of that air doesn't go through the IT equipment, so it doesn't warm up at all. And the two airflow streams mix back together, resulting in a 20-degree increase from where it left the cooling unit. And then that 20-degree warmer air returns to the cooling unit, gets cooled off 20 degrees, and it repeats its cycle. So in your room, you have to have a little bit less than twice as much air moving through the IT equipment. I'm sorry, a little bit less than half as much, a little bit less than twice as much air moving through the cooling units as moving through the IT equipment, and everything will be a steady state. And the only way to change that is to change the cooling units and change the design of the cooling units, so that physically change the cooling units so that they are ones that have a higher delta T. In that case, you could supply less air, but that's obviously a very expensive approach. Most computer rooms are similar to yours. But also, if you look at the average delta T of your IT equipment, it's likely not an average of 35. There will be a lot of IT equipment with lower than a 35-degree delta T. So it took a lot of time to answer that question. Very good question, and hopefully helped a number of other people as well. And I see right below you asked, Tim, again, do you increase the CFM to address the delta T? And as I explained, exactly, that's exactly what you have to do. But you don't have to go change and increase the CFM. I would bet that that's already happening, that you already have significantly more CFM moving through your cooling units than moving through your IT equipment. If you didn't, you would have a problem, and that would be obvious. Next question, do most PDUs require cooling air? Should they be contained? That's a good question. PDU manufacturers will say two different things. If you say, I want to buy a PDU and place it on a slab with no cooling from a raised floor, the manufacturers will say, sure, no problem. But then when you have it on a raised floor and you have a big hole under it that you want to close, the PDU manufacturer will say, oh, no, you can't close that. It has to have air flowing through it. So I've had this happen on a number of sites. The answer is that they require way less air in most cases than they're getting. So if there's an entire missing tile underneath a PDU, they may only need a 4-inch diameter hole to provide enough air to keep them cool. And the way to do this, to really refine this, is to work with the PDU manufacturers, and you really sometimes have to beat them up and push back on them to get some clear information about how much air is required. It all comes down to internal temperatures and not causing the PDUs to overheat when they're fully loaded. And you definitely don't want to cause that situation. Someone asked for a quick refresher on the CCF figures. Real simply, CCF is calculated by taking the total rated cooling capacity in the room and dividing it by 110% of the IT load. So if you have 10 30-ton cooling units, 30-ton cooling unit can remove about 100 kilowatts of heat. So about 30 tons is equivalent to 100 kilowatts. So 10 times 100 is 1,000 or 1 megawatt of cooling capacity. But if your IT load is only 450 kilowatts, you add 10% to that and you get to about 500 kilowatts. So 1,000 divided by 500, you got a CCF of about 2. We also have the calculator on our website if you want to utilize that tool. And I'm also happy to provide a Excel spreadsheet with some data collection tools and calculators to calculate a number of other airflow management metrics. If you want to get in touch with me directly, I'll send you that Excel file. Looking at some more questions, really appreciate all your questions, and I'll get to them as quickly as possible. What control strategy do you recommend to match CFM to cooling unit with CFM of IT demand? Great to see these questions. The strategy is to understand what the CFM is of the IT equipment, and then look at the CFM of all the cooling units, see how different they are, and the difference is the bypass airflow. And if you discover that they're very different and you have 2 or 3 or 4 or 5 times more cooling moving through the cooling units than moving through the IT equipment, then you start to look at, well, where is my airflow management lacking? Do I have blanking panels in every opening in the cabinets? Are the rails in my cabinets sealed to the sides of the cabinets? Is there space under the cabinets? And then looking at the raised floor management and improving airflow management. And the more you improve airflow management, the more you can cut back. You can reduce the flow rate through the cooling units and get them as close as possible. Ultimately, you'll bump into that delta T consideration between the IT equipment and the delta T through the cooling units. Also looking at some more, we have a question, how does the delta T relate to the cooling tower approach temperatures? That gets fairly complicated, a little too much to discuss here, obviously, but the goal of improving efficiency is, of all the systems, is to get the operating temperatures, and that would be also would apply to the cooling tower approach temperature, get those temperatures as high as possible. And it all ties back to airflow management and supplying the warmest possible air to the servers without causing the intake temperatures to increase. So one of the misconceptions is that I can't raise supply temperature in my computer room because I'll start overheating my equipment, or the reliability will drop of the IT equipment. It's true that the warmer the air going into the servers is, the less reliable they will be, but that number can often be very small and doesn't even show up in the life cycle of servers sometimes. But that aside, by improving airflow management, you can supply warmer air without increasing the intake temperatures to the IT equipment and causing no downsides. What control strategy do you recommend to make CFM to cooling unit with CFM to IT demand? There are a number of different control strategies, and they all, what's most appropriate depends on the configuration of your room, whether it's slab or on a raised floor. Also, how extensive is the airflow management in the room. The simplest way to control CFM of variable speed fan units is on static pressure under the raised floor, but this will only pick up how much open area there is in the raised floor. So if you install a new row of IT equipment and you take out a bunch of solid tiles and install perforated tiles, then the static pressure will drop, the sensors will sense that, and they'll speed up the fans to accommodate the extra holes in the floor, and you'll have a consistent static pressure under the floor, and you'll have a consistent flow rate of conditioned air out of the supply tiles. But what that method doesn't pick up is it doesn't pick up variations in the IT demand of a particular row or contained dial. That requires measuring on the static pressure difference between inside the contained cold aisle and outside the contained cold aisle. So hopefully that answers your questions. Some of these are a little bit complex and difficult to try and answer quickly over the phone. and I'd be happy to discuss them with you over the phone or through email. Next question, regarding the rack-top baffles, is there any accessory to install when we have different heights of cabinets so we can install all the rack baffles at the same height or level, or does it not matter? The answer to the question is it probably doesn't matter much. With baffles on cabinets that are at different height, you'll be in a far better position than no baffles at all, and we'll be able to realize quite a few benefits. Having the baffles at the same height in some situations may be better, but the incremental improvement is going to be very slight. And it's also possible for us to do some custom solutions, and happy to discuss those with you. The question is, what happens to the delta T when the containment is in cold corridors? What happens to the delta T when the containment is in cold corridors? So one of the first things that I discussed is that the delta T of the IT equipment will be the same regardless of the airflow management in the room. So delta T of the IT equipment will be X, and then you put in full cold aisle containment, and the delta T through the IT equipment is still X. But what it allows you to do is full cold corridor containment is likely going to reduce the highest intake temperatures significantly and make the intake temperatures much more consistent. And that gives you the opportunity to raise the supply temperature and increase the efficiency of the system. But it won't particularly change the delta T of the IT equipment. It will give you the opportunity to increase the delta T of the cooling units. So when you're running way more air through the room than is required by the IT equipment, then the delta T of the cooling units is lower. The delta T of a lot of cooling units running at partial capacity is only 5 or 10 degrees or somewhere in that range. And so if you increase airflow management, improve the airflow management by installing cold containment, cold corridor containment, then you can reduce the flow rate of air through the cooling units, and that will give you the ability to increase the delta T across the cooling unit coils, giving you more capacity and more efficiency. Hopefully that was clear. Fairly complex, again, issues to try and address here. Next question, is there an efficient way to cool down special hardware that takes the inlet air from side, not the front, in a cold aisle or hot aisle environment? Yeah, absolutely. There's a number of switches out there and other devices to take air in the side and blow it out the other side, or in the back and out the front. And all of these reduce the ability to have an efficient room. We don't have any products to address that. There are a number of manufacturers that have sheet metal kits for different configurations to retrofit those devices so that air is being pulled from the front and exhausted out the back. Quite often that requires a 1 or 2 U of free space above or below the device, or different cabinet designs, depending upon how much space there is on the sides of the cabinet. So there are systems out there that you can research and discover for improving that, and I do highly recommend for everybody to get that non-conforming airflow equipment into a standard front-to-back configuration, because it'll go a long way in improving the efficiency of the whole system. On the webinar that we did last week, we discussed a specific case where changing just a small percentage of the cabinets in a room from side breathing to front breathing enabled dramatic improvements in the efficiency of the entire room. Next question, are Tier 3 requirements of Uptime Institute taking into account good airflow management practices? It's been a little while since I was closely related to evaluating Tier 3 or any of the tier requirements of the Uptime Institute, but my understanding currently is that they do not relate to efficiency at all. So it's possible to have a very inefficient site that is Tier 3, that is Tier 3 certified even, because the tier ratings relate directly to the robustness, the redundancy, the concurrent maintainability, and the fault tolerance of the infrastructure, of both the electrical and mechanical. So it has to do with concurrent maintainability and fault tolerance, and not about efficiency. And again, just to wrap up, I think we've gotten through all the questions, and want to say to everybody, please, if anything I shared wasn't very clear, contact me directly, and happy to discuss it further. And you're very welcome. I'm glad you found it valuable.
Thank you, Lars. I would just like to remind everyone that we will be sending out an email with both the slides and the recording of this presentation. So keep a lookout for that, and thank you all for attending our webinar today.